So we got our definition. So now the fun part. So now let's do an energy balance on a control volume and see how we can develop temperature equations for this heat exchanger. Because ultimately, like, you need to know the local temperature of the fluid in order to decide how much heat's transferring between the streams. Okay, so we're going to develop the temperature equations, solve them, and hopefully we get to a point where we can just compute the total heat transfer either locally or over the entire device. All of this, like, you can sort of see we're kind of putting together pieces. So we have this overall energy balance. We have this conductance. Now we're going to do a control volume energy balance, control volume analysis. These aren't like separate. They'll all come together in the end because basically we have to solve all of these things together as a single set of equations to figure out the performance of the system. All right, so we'll come back and like get these other pieces later. All right, so we are now doing a control volume analysis to develop a model for temperature as a function of x, as a function of position. All right, and we're developing that both for the hot stream and the cold stream. So let's say up here on the top, can't remember if I did this, so let's call this the cold. Let's call this down here the hot. So I actually want to have two models or two predictions, TC and TH. They are related to each other, right? Because they're part of the same system. So we're going to end up solving this coupled ODE, all right? It's not as bad as it sounds. We have to draw a control volume, and we want to make sure the control volume lines up for both of these streams. So let's pick some location. Let's just do this here. So I'm going to draw a control volume for the top, and I'm also going to draw a control volume for the bottom. I'm going to say the control volume goes from x to x plus dx, and it has a width of dx. I'm also going to say that there is a heat flow, right? We know that there's, well, we drew it hot and then cold on top, so we know there's a heat flow, let's say, in this direction. Does it really matter if we say it's hot or cold? Not really. We just have to be consistent with how we draw it, right? Or how we draw it and do the analysis. Okay, so we do this, now we approach this the same way we did internal flow energy balance, but we're just doing it twice. So let's start on the hot side and kind of work things out. So we have, going into the control volume here, we have the capacitance rate C dot H times TH at x. Leaving, we have C dot H TH at x plus dx. Right? Let's assume here that C dot H, the mass flow times the specific heat, is constant. Right? That's not changing. It can change. You can deal with it, but for now, let's just assume it's constant. And then on the cold side, we have flow going this way. So at the top, on the right, let's say going in, we have C dot C times TC. This is, like, so the question is this x or x plus dx? Well, we're setting up a single, like, aligned control volume. So x has to be the same in both models. So it's an x plus dx. Right? Hopefully that makes sense. We're focused on like how we've drawn it and where we position things. So now C dot C, TC at x over here. So in one case we have like x corresponds with going in, and the other case it's x corresponds with going out of the control volume. But okay, so we just walk through this now, and we're going to get the control volume energy balance, and then just develop an ODE from that. So here I say, how do we incorporate UA? All right, well, this is all getting to that. So doing the cold side energy balance, right? We have kind of two coupled control volumes, so we have to do two control volume analyses. That's going to look like this. So it's just in minus out equals 0. So coming in, we have C dot C. We have TC at x plus dx. We have leaving C dot C, TC at x. From the cold side, we also have coming in the heat flow. Okay, so plus, I guess I didn't label this. So that arrow from hot to cold, for a differential volume, let's call that dq, dq dot. It's a differential component of the heat. So we have coming in this dq dot. All that equals 0. Okay, let's see, we can expand out as we normally do. So this becomes, expanding the first term, c dot c, tc at x plus c dot c, tc at, c dot c times the differential, dtx, dtcx, dx times dx, minus c dot c tcx plus dq equals 0. Okay, so then we can cancel out this term and this term, and we're left with, bring the dq to the other side, so dq dot is equal to minus c dot c dtcx dx times dx. Give you a chance to write that down. Okay, so that's the cold side energy balance. We can do the same thing on the hot side. Make sure we're keeping track of the fact that now dq dot is going into the hot control volume as opposed to the cold side where it was leaving it. So it just changes that sign. But what we end up with on the hot side, so hot side down here, I'm just going to write out the expanded form. So that's c dot h thx minus, expanding it out as c dot h thx minus d thx dx dx. Now minus dq dot equals 0. Cancel, cancel, and then we have dq dot equals minus c dot h dthx dx dx. Okay, so let's see, we have this one here, and we have this one here. And they're related to each other, right? Like they're related by the fact that dq dot is the same in both cases. It's a single value of dq dot.